So in this last video, we're gonna talk about some practical uses that we have for duality in the context of linear programming. In particular, looking at how we can read dual values as marginal values and then talk about the dual simplex method. So this notion of looking at duals as marginal is actually quite important for real applications of linear optimization because it's a way to measure the value that a given resource has in the context of the problem. So you can use those to price the value of capacities in a capacited system. You can use those to price the value of commodities. You're going to see some examples where we price supply capacities and energy tariffs, like the price of electricity, which is in real world they actually using dual information. And all of this comes from the following idea. So let's look at this non-degenerate optimal basic feasible solution that has its corresponding basis B. And therefore, we know that we can calculate the x like such. Okay? And it's strictly greater than 0 because it's non-degenerate. So let's assume that we wanted to make a marginal perturbation of the vector B, but really, really small, just in a sense that we're almost trying to capture what is this gradient kind of like value. What would be the potential change moving in a perturbation directed to D. But in this case, we're thinking of it as a scalar. Actually, you can think of this as the vector B, but when we actually do this and we want to look at individual values, we'll look at individualized. But for the sake of what we're developing here is just to show you that suppose we apply this variation G, and that will mean that our value B minus 1B gets changed like this, but we want to make this small enough so this still holds, okay? Because x is optimal, we know that these reduced costs are all positive, no negative, okay? And that will mean that if you're doing this marginally and not changing feasibility, you're not influencing which is the optimal basis, because you can see here really any influence that you have because of the vector B. And that is kind of like, it is associated with this. It might be weird when you hear that at first, but basically, suppose you have two constraints here, okay? And what you're doing when you're changing B marginally is getting this constraint and moving it slightly on its current position. That's what changing B in this constraint would entail, right? But you see that if the movement is marginal enough, you're not changing which are the constraints that are active. You can't just by marginally moving this change what is the optimal basis, unless suppose you had another constraint like in blue here, and then you do a movement on that is big enough to move this away. So then what you're actually going to be making is this basis infeasible. And that's what we're preventing when we say this. So for marginal changes of this, you would still remain with this selection for the basis in terms of what are the active constraints. So the actual influence then you would see is in the optimal value, which we know that can be written like so. This is just how we write P, and then the multiplication of PB and PD, and specifically this here is giving you an idea on how you can use the dual values. And specifically, the value of the dual variable times this marginal variation would be exactly the potential change you see in the objective function, meaning that you can look at the value P as a sort of a marginal value or a marginal cost for the resource I, to which is a constraint, to which this P is associated. So pretend I is a constraint, say, related to the capacity of a given arc. The dual variable that is generated associated with the constraint that define the capacity of the arc would be this marginal value or having the capacity expanded, given you have an optimal setting. So this is a really practical interpretation of the dual values. You will see that we can kind of see those in the tableaus when we're doing calculating simplex methods, and basically most simplex implementation codes will give you these values fairly, in a fairly straightforward manner. And I'll show you how they pop up as also on the simplex tableau shortly. So that's it. That's the practical interpretation of the dual variable values as the marginal costs. The other use of duality is in linear programming is this notion of the dual simplex method. So dual simplex method is, as the name suggests, a dual method. And in optimization, we tend to classify the methods we have as primal or dual methods. And the main difference is related to what they maintain and what they seek. If primal methods, like the simplex method, they maintain primal feasibility, so they start from a feasible solution and look for new solutions while maintaining primal feasibility, while seeking dual feasibility, which means primal optimality, as we see in the last video. And dual methods, they do the other way around. So they maintain dual feasibility while seeking for dual optimality, which comes from observing primal feasibility. So because we have this primal dual relationship, we can, once we give a primal feasible solution, we can search for a dual feasible solution, and that's a primal method. Or if we're given a dual feasible solution, we can find a primal feasible solution, then that's a dual method. And the dual simplex is a dual method, and the primal simplex or simplex method is a primal method. So like we said, when we talk about the simplex method optimality condition, which is given by whenever your reduced costs are non-negative, can be, we saw now, it can be readily understood as a dual feasibility condition, right? We know that this is our vector P. If we move this to the other side, you get exactly the dual feasibility condition that you would have when you get to your primal problem in that canonical form we defined and derive its dual. So if you think about the dual simplex method, what we're going to do is the other way around. We're going to start from a solution for which this is already observed. So dual feasibility is observed, or it's almost like a solution that starts satisfying optimality conditions, but it is a solution that is not primal feasible. So the primal feasibility constraint, which in our case for the simplex method, the only one that we really have to worry about is the non-negativity of the basic variables. This is going to be what we're going to be searching for. So basically we will allow ourselves to start from a solution that perhaps satisfy optimality conditions, but they do not satisfy primal feasibility. And what we're going to do is iterate while maintaining dual feasibility. So we maintain dual feasibility while searching for primal feasibility as we iterate. So what does that mean in practice? Well, it's the dual simplex method works exactly like the simplex method, in which we start from a basis, we decide what is the pivoting we should be doing, and we perform elementary row operations to pivot and change the basis, the basic matrix, and at the same time updating the list of basic indices. So what makes it different now is that because we'll have basic variables with negative coefficient, negative values, meaning that they are non-feasible in a primal sense, we're gonna pick those to remove from the basis. So we'll remove from the basis variables that don't satisfy primal feasibility. Just like in the primal simplex, we remove from we want to add to the basis those that do not satisfy dual feasibility, or they have reduced costs that are negative. And what is gonna enter the basis is that non-basic variable that once it enters the variable, the basis, it doesn't turn the reduced costs negative. So it maintains dual feasibility. Okay. And how we devise that? Well, the choice of the variable that leaves the basics is obvious. We just look at those that have a negative value at that basis and pick that to leave. To enter the basis, we have to adopt a sort of a tailor-made criteria to select which of the non-basic variables can become basic without compromising dual feasibility conditions or primal optimality conditions. So let's think of a simplex tableau here, because it's kind of easier to show what I mean with these. So suppose that we look at our simplex tableau and we picked the row L, to which we're observing xb being negative. And when I look at the row of the tableau, each of those elements below each of my variables, I'm calling v1, v2, all the way to vn. And then at the last column on the right, assuming you use as a reference the right-hand side like I do, so the last column on the right will be the value of the variable. And what we're going to do is, of all the components of the row, with exception of the rightmost element, I will look for those that are negative. And among those that are negative, I'm going to pick that shows me the smallest ratio between the reduced cost and that element. Remember that we saw this last class that the top row of your tableau shows you the reduced cost element, the C minus CB, B minus 1, A for that column. And I'm going to pick the minimum of them, just like we do with the ratio test in the primal simplex method. And once I've selected who is entering, who is leaving, pivoting is doing exactly as you do. You're very good at doing it now. Basically turning the column of this non-basic variable that you just chose to become basic, make it become the EI vector, meaning that for the column, for the element that intersects the column, for this becomes 1, and all the others all other elements in that column become 0. If this is a bit confusing by now, I'll have a numeric example in Tableau format to help with that. And this is just showing the following. The reason why we're doing so and why we only want the negative ones is because we want to make sure we maintain the optimality condition, the primal optimality condition, or the dual feasibility condition of having no negative reduced costs. You can see here that the way we're doing this is such that this ratio is going to be the smallest ratio among them all. This is the J prime is the one I'm selecting. So I know that this is true. So if I multiply this on that side and move things accordingly, I get this condition, right? Which implies that when I add, because I'm taking the module, but when I add the actual value, because this thing is negative and I'm only picking the negatives, this is guaranteed to be true. So it works exactly like the ratio when we look at the B's and divide. In the primal simplex, we're doing B divided by these terms. It's exactly the same way, and we're trying to make the terms on the B not become less than 0. This is exactly the same thing. We're trying to make sure these things, the reduced cost, don't become less than 0. So same mechanic or same mechanism. Okay. And that's it. That's all you need. You stop either when um, if all your components of that row associated with the non-feasible basic variable, if none of them are negative, that basically telling you that your dual is unbounded. And we saw this earlier in an early video that a bounded dual means a infeasible primal. We even proved that. Or it might be so that all your it is the case, but then all your basic variables are primal feasible. And that means that you found primal feasibility while maintaining dual feasibility. So primal feasibility plus dual feasibility means optimality. So you found a primal dual optimal solution, which has this form. The X like so with basics and non-basics, and the value of your dual variables become like so for your basic and non-basic variables. Okay. And that's it. So another thing to point out is that your objective value is going to be monotonically increasing, and the reason for that is because you're adding this thing, which is negative because this is less than 0, to this thing as represented in your tableau. But remember that your tableau there, your objective value is actually the minus of this. So we basically say you are at the point you have -3, then it's gonna go to -10, which means that it's increasing from 3 to 10. It's just that's why I personally don't really like tableaus that much, because they may be confusing depending on the convention you adopted. We are adopting the same convention of the textbook, and the convention of the textbook is such that it's looking at minimization problems, and because of that, this thing has a negative sign, and the workout, it works out that then is adding to this. If it weren't, then the resulting outcome is the same. It means that, remember that we are in the dual space. I'll do that picture, make that picture once again that we did in the beginning. So this is what we're looking for, and we are talking about dual values. So dual values are here, and it's natural that the objective function is increasing because we are going towards the optimal. Okay. So this is one point, and the other one is that termination is guaranteed when all your reduced costs are positive, no negative really, because that could be degeneracy. And I think that's the next comment there. In case, so you might have some zero reduced costs associated with some non-basic variables, and that would mean that your algorithm might cycle, because you might make that non-basic variable basic without changing your objective function. And that's a consequence of dual degeneracy that happens just like primal degeneracy. And in fact, dual degeneracy means that your primal has multiple solutions, which I think is the next point. Yes. So your dual degeneracy means that you have multiple primal solutions, multiple optimal solutions for your primal, and basically means that you can make the non-basic variable basic and not change the objective function. So you have two bases that are representing the same objective, same solution, and that's just that. So here is a summary of the dual simplex method. I'm cheating a little here. It's exactly like the primal simplex method. The only difference really is the way you choose your basic variable to leave and your non-basic variable to become basic. And I'm overloading this word form new basis B, because to form new basis B truly means get whatever representation you have of your B-1 matrix and update it. Or if you're using tableaus, you update your tableau accordingly. So this is overloaded in the word form. It's implicit in the word form, the new basis. Okay. Right. And some final last remarks here. So we'll see this again and again, a few times at least in this course still, when the dual simplex is most useful. To be honest, most of the time your solver will be using dual simplex instead of primal simplex. And one of the main reasons for that is, well, there is some reasons associated with numerics and performance, but one of the main reasons for that is associated with the fact that typically dual basic feasible solutions are trivially available, while primal feasible solutions require phase one, which is computationally more expensive. Every problem that you have, say this is x1 and x2, okay, every time you have, say, a greater than equal than constraint that is not touching the origin, so it's not redundant, so it gives you something that looks like so. This solution, we saw that makes the 0, 0, the origin, not be a basic feasible solution anymore for the primal simplex. But typically when you're minimizing, so suppose you have a vector C that looks like so, this point satisfy optimality conditions, in the sense dual feasibility conditions, in the sense that is more optimal than it could because it's past the feasible region. So this point is typically a point that satisfies dual optimality conditions. So it means that you don't have to do a phase one to start dual simplex. Another reason why you want to use dual simplex is when your B, remember we talked about the B changing? It might be that you are in a situation that your problem from today for tomorrow changed so much that your B actually went beyond becoming feasible. So doing that drawing I did again, let me move just a bit further up there, like that. That's fine. You're gonna not see some of it, but it's fine. So yeah, I did this drawing where I had two constraints, and I was saying that this is the basic variable, and I had, say, a third constraint there. And then once you start moving this too much, it might be so that this becomes infeasible right here. Okay, so that it would be the new feasible region. So what you basically have is that this basis is there's no reason, like we said, there's no reason why to believe that it's still dual feasible. There is no reason why you could make it not dual feasible. There are, but in a general case, this is still close enough, so it's still dual feasible, but it's not primal feasible anymore. So you have a perfectly good candidate to restart to dual simplex. So you don't have to start from scratch. You can just start your algorithm from here, and hopefully one iteration will take you to the new optimal. And it usually is a small number of iterations. And finally, when you have additional constraints being posed, and that actually represents two really, really important cases that we'll look into later on. One of them is when you use simplex method to solve integer programs with an algorithm called branch and bound that we're going to cover in a couple of classes, in a couple of weeks. And also when we talk about something that is called Bender's decomposition, which also benefits from the use of dual simplex as well. And that we're going to talk about, I think, in our lecture 10, if I'm not mistaken. So yeah, so it's a very useful algorithm. To be honest, probably the most used algorithm in terms of LP nowadays. So here is an example for the dual simplex. So it's a minimization problem with greater or equal than constraints. And so in order to use dual simplex to solve this, the first thing we need to do is to get a basis out of that to start with. And the best way of doing such is do something we couldn't do in the primal simplex, which is just multiply this by -1, multiply this by -1. So they become less or equal than constraints, and I can add slacks with positive coefficients. So I get what is here before. -2 here and -1 here. Before I couldn't do this because this would be infeasible and primal simplex require primal feasibility. But now, because I don't care about primal feasibility anymore, I can do this. And notice what is interesting is that these two select variables, they are giving me a basis to start with. So here's my identity matrix with x3 equals -2 and x4 equals -1. It's just like saying that I have slacks that are taking negative values. And that allows me to start from the point where x1 and x2 are 0, which I couldn't before. So I can use that as a starting basis. And you can see here that everything in this line is my reduced costs, and they're all positive. So this is dual feasible because it's a minimization and they all have positive coefficients. Yeah. And here is just, Tableau. How do I decide what variable I'm going to leave the basis? I look at these. One way is just picking the largest, kind of like Danzig rule, or you can just pick, the smallest index. Recycling ideas kind of apply similar sense. Here I decided to pick -2, so that makes this the variable leaving the basis. To decide who is going to enter, I have to look at my v vector, which is this, and see which components are negative. I have these two. So I have to do my ratio between this and the module of that, this and the module of that, and pick the smallest, which in this case would be half. So this column with this row gives me this pivot element. So that means that this thing has to be modified with elementary row operations such that this becomes 0, this becomes 1, and this becomes 0. There's nothing to be done here, so I got a row for free. To make this 1, just multiply by 1 over the value you have here. To get this 0, you get this row. You multiply by 1 minus the values here, and 1 over the value that is here, so that becomes 1. And then you subtract from this row times minus this value. Or you subtract from this divided row minus this value, times this value, which in this case is 1, so you don't have to multiply. You just have to multiply by -1. And then you add up there, and what you get is something that looks like this. And look what's happening here. Now I'm at the primal point x21, x10. I still have one negative number here, so now it's obvious that this is my row. Because my vector v only has one negative element, this is my column. And now what I have to do is convert this into 1 and convert this into 0 and 0 with elementary row operations. Converting this to 1 is simply divide by what is in here, -1. Dividing by -1 is just multiplying by -1. And then what I'll do is multiply by minus what is in here and add the row there. Multiply this row by minus what is in here and add that row there. So that gives me these zeros. Which takes me to the next point. And you can see that my reduced costs are never turning negative. You see, because I'm maintaining optimality conditions or dual feasibility condition. And you can see that my objective function is started at 0 and it went to 1 and then it went to 3/3. So it's increasing. Okay. Yeah, and then in this case, now I found primal feasibility. I can stop. This is optimal. Dual optimality. Dual feasibility, primal feasibility means optimality. And that's it. We can also see that how does that I have a picture showing how this actually is working. So here it is for the primal space. So let's concentrate on this picture first. And this is exactly what we've done in our steps. So we started with 0.00, and then x2 became basic and we went to the 0.10, and then x1 became basic and we ended up at the point half and half. So this is the feasible region. I started with a feasible point, so that's why my slacks were negative and went from here to there and stopped at the optimal points there, which is given, can show this is my objective function, and because I minimize, I want to go that way. Now, if I looked at the dual space, one thing that I could do is simply write the dual of this problem and look at the and solve it with a primal simplex method. That would show us the following. I would have started from a 0, 0 point. You'll see that it doesn't need two phase. Then it takes me to the point half 0, and then we end up at point half and half. And you can kind of see these values when you look at the tableau and focus on these elements. So I start from 0, 0, then I end up in half 0, and then I go to for half and half. And the reason for that is that these terms, they are the reduced costs. But it turns out that because for the slacks, I am adding elements here that are with coefficient 1. When I multiply by the column A, that term CB minus, C minus CB be a minus 1A. So this is the identity, the column of the identity matrix, and this is 0 for these slacks. So meaning that I end up with something that looks like this, which is exactly minus P. Now, this is an issue though, because in order for this to match in sign with the actual value of dual variables, it really depends whether you started with a greater than equal or less than equal constraint, and if you multiplied it by minus 1 or not. Because we did this trick of multiplying this by minus 1, it basically means that these variables, these values will not truly match your dual variable signs. So basically, these are the absolute values of your dual variables, but sometimes, like it is the case, your dual variables would actually be returned from your simplex method with a negative in front of it. So they would be 0, 0, minus half and 0, minus half and minus half. But because I wanted to actually look, have a nice picture of them on the other side, if you go about and write the dual for this problem and then solve with primal simplex, then you'll get positive p's, and you do see this picture like it is here. It's just a small observation on that. Sometimes, so Julia, for example, it has a function called shadow price and another function called dual. So in this example, if you ask the shadow prices for this constraint or this constraint, you would get these values. But if you ask for the dual of these constraints, you're actually going to get something with a minus in front of it. And general rule is, if it's minimization, greater than or equal than constraints have flipped signs. And if it's maximization, lesser or equal than constraints have flipped signs. That's all. And it's just because of the way things are conventioned when you write the method. Okay. I hope that was clarifying in terms of how the dual simplex work and how we can use it to solve linear optimization problems. So that's all for this week. I hope you enjoyed the lectures, and looking forward to seeing you on Thursday on our session online. Bye-bye.